During this video, I want to introduce the idea of an energy bar chart as a representation that helps you think through what energy transformations are happening in a given situation. So, if you like, you can think about this a little bit like the free body diagram was for forces, where it really helps you think through what's happening, and it focuses your attention on some of the most important aspects of the problem. So I'm going to start with a really simple scenario. I'm going to, even before I start, I'm going to assume that you know the formula for kinetic energy. So this is just a little recall. Hopefully it's a recall. I don't think black is showing up super well, so I'm going to switch colors. Find my blue. So I'm going to, kinetic energy, just call K, is 1/2 mv squared, and gravitational potential energy is mgh. There are lots of other types of energy. These are the two we have formulas for, but in the energy bar chart, we will often name other types of energy without necessarily having a formula for them. And I'll show you that example right now. So, so this is just recall, right? So example one, I have a box, okay? It's initially moving at velocity v. So here's my box. This is my initial moment. And then my final moment, the box is going to be over here, and v equals 0. So maybe before this, earlier over here, somebody gave this box a push, but right now it's just sliding along, and it comes to rest. This is my final moment. So I'm actually going to label these, and as you're taking notes, you should label these as well. This is my initial moment and my final moment. Whenever we're going to do conservation of energy, it's going to be really important what you choose to be your initial moment and your final moment. So this first representation is just a diagram. It's two snapshots of the motion. So this is snapshot 1, this is snapshot 2. I could have probably drawn them on the same line, but sometimes the scenarios get complicated enough that you really want to draw them two separate copies of them, even though it can seem a little annoying to draw it twice. It can be really worth it. So this is my diagram, and below this, actually I think I'll get rid of this eraser part. Sorry, I'll erase this part and work up top, but in your notes it'll probably be below. So the first thing we're going to do when we draw this diagram, the second thing we're going to do is actually draw our energy bar chart. And in order to do that, we basically have our initial moment here, and I'm just going to draw a line there. You'll see where it's going in a minute. Final moment here. Okay, so for every type of energy that exists in the initial scenario, we're going to draw a bar. So we know there's velocity. We know that kinetic energy is 1/2 mv squared, which means kinetic energy is never negative. So this, because the v is squared, so even if the v were a negative number, when you square it, it'd become positive. So kinetic energy is some amount. And it doesn't matter how big really we make this, but I'm going to label it like this. And I'll put the K right underneath it. So there's our kinetic energy. Do we have any other types of energy? No. So I'm just going to leave that blank for right now. But eventually I want a column for every type of energy that exists, either in the initial or in the final scenario. So you'll see what I mean in a minute. So finally, where has that energy gone? Remember, energy cannot be created or destroyed. That's the language of conservation. And so however much energy we drew here has to exist in one or more bars in our final scenario. So where is it? Pause the video for a second, see if you can come up with a name, and then I'll be back. Did you really pause it? Pause it. Think about what the name is for the type of energy over here. Okay. You might have called it heat, but to be friendly to the chemists, we're going to call this thermal energy. So I'm going to draw a bar. I'll give it a different color. If you're not working in colors in your notes, that's totally fine. It doesn't really matter. But we might as well. And I'm going to call this E with a TH subscript, E thermal. And ideally it should be the same height. You know, this is just like a free body diagram where the arrows, we don't take a ruler to the arrows and measure exactly how long the arrows are, but visually, this is a visual representation to help us, you know, kind of see where the energy transformations are. So we kind of want them to look roughly the same height. And now I want to make sure, so this may seem a little picky, but I want E thermal to show up on both sides, but there's no E thermal over here. E thermal. And I want kinetic energy to show up on both sides, and there's no kinetic energy here, so I'll just draw kind of like a thicker line at 0 and say kinetic. Okay, where did this thermal energy go? Thermal energy means something is like warmer to the touch. Thermal energy means something has a higher thermal energy means that either something has melted or it has a higher temperature. Melted or boiled, it has a higher temperature. So in general, and for our purposes, we're not melting or boiling the floor. So it just means the floor has warmed up. So there's some thermal energy that is now distributed along here. We've actually warmed the floor up a little bit, and we've warmed up the bottom of the box. And you know, your demo for this is just put your hands together, rub them, right? And then feel against somewhere sensitive, like your cheek is a pretty sensitive area of your skin. You can feel that your hands are warmer. You can feel them just from your hand, but you can also feel from like a neutral place that, oh yeah, your hands are warmer. That's thermal energy that's been converted from the kinetic energy, the moving energy of my hand. Okay? So this is the energy bar chart representation. This is just the diagram representation. And for starters, in problem solving with energy, I'm going to want you to do I'm going to want you to do both of these every time you do a problem, for starters. Later we'll talk about which problems really need it, and we'll have certain problems where you can see it because of what's going on. But it really helps you think through what are the key, it focuses your attention on the energy transformations. And you might think, well, that's pretty obvious. It's the simplest bar chart you can imagine. And I agree with that, you know. So now what I'm going to do is I am going to drop a Kleenex. Dropping a piece of paper. Okay. So here's my initial, I have a piece of paper that looks like this. I'm holding it at rest, so V equals 0. This is my initial scenario. And then my final scenario, the piece of paper, I'm going to pick the moment before the piece of paper hits the ground. So it hasn't hit the ground yet. It is moving down, so V. So it's got some velocity downwards. And what I want you to do is draw an energy bar chart for the types of energy that the paper has. So energy we're focusing on this piece of paper as our object, the thing we care about. Types of energy, and how big you think they are. Some of them may be 0. Types of energy here, how big you think they are. Pause the video, try to make your own diagram, and then come back. Okay, hopefully you've done that. So initially, I don't have any velocity, so kinetic energy is 0. You might have just left it off your diagram, and that's okay. But I know that later I'm going to have it on my final diagram, so I'm going to put it on both, and you should always put it on both. If it shows up on either one, if the energy shows up on initial or final, put it on both. Kinetic energy is 0. I've got some gravitational potential energy because the paper has mass, and remember UG is mgh, so I've got some amount of gravitational potential energy. I guess in my world of colors, it's going to be this color, which amazingly enough is green to me, but I think when you side light it with fluorescence, it looks blue here. I don't know. Talk to your neighborhood friendly chemist and ask them why green expo marker looks like really fluorescently blue-violet to me. Anyway, off topic. So gravitational potential energy, that's here. I think that's it. I think I've got those 2 types of energy. Well, I've really only got 1 type of energy. So final scenario. Now I have some kinetic energy, okay. And I drew this a little bit off the ground, so it's up to you. Let's say that because it's a little bit off the ground, it still has some UG. Later, if we're solving problems, we might want to get it all the way where it's just barely off the ground and we can take that height to 0. But just based on this diagram, this visual, let's say that it still has some UG. So it has some kinetic energy, but it better not have the same amount. It better have less, because it's still got a little UG, right? UG. And these two, the question in my mind is, do these two add up to be the same height as these two? Should they add up to be the same height as these two? So the question, I'm going to have you pause the video in a second. The question is, should the sum of these two heights be the same as the sum of these two heights? Okay, hopefully you've thought about that. In some situations, it depends on what you drop, right? If I drop this expo marker, it's pretty close to these heights being the same as those. But if I'm dropping a piece of paper, we know that air resistance is going to be a factor there. And in fact, you lose energy into the air, and it's in the form of thermal energy. And so there's some amount, I don't know how much, there's some amount of E thermal. And so over here, I'll draw 0 and I'll draw E thermal. So here's my energy bar chart. Kinetic energy went up, gravitational energy went down. If I'd drawn this a little lower, it could have gone all the way down to 0. But we picked up some thermal energy, which was our air resistance or drag, whichever one you want to call that. Because we know that the air resistance is a factor here. This piece of paper is not falling down as fast as the marker, so there must be, air resistance must be a factor there. Okay, so those are two examples of the energy bar charts, and also drawing your initial and final diagram. So initial and final diagram for each energy problem, and then initial and final energy bar chart. These don't need to be numerical for starters. You may find later in the problem solving process that you want to put numbers on some of these bars as you figure stuff out. But that's totally fine. I would encourage that. But don't feel like you need to know the numbers. It's a little bit like the arrows in the free body diagram. You might not know exactly how long they are when you first draw them, but it helps you think through where is the energy starting, where is the energy going. And that's the point of the energy bar chart.